Hey folks, Sega Sonic fan here. This is part of a new series I'm trying where I'm going to explain some of my digital and analog electronics knowledge to people. Hopefully some of you will find this helpful. It'll also help me out a little bit to kind of clarify some of my knowledge on stuff. And yeah, a couple caveats before I do this, before I share and kind of teach online here. First is that I am entirely self-taught. I have had that many hours of education in a university setting for electrical engineering and digital circuits. I've been doing this for about 13 years, but all my knowledge is just me searching and watching videos like this, which is part of why I want to do it, because I want to give back to people that are learning in the same ways that I did from really generous people that made videos and answered questions online for me over the years. And so that's the first caveat. And the one thing I'll say about that too is that I might have some gaps in my knowledge because of that. And the advantages of that is that I feel like I am a pretty good teacher for a lot of stuff. I have a way of kind of explaining that's going to be really different and hopefully less dry than you would get in a university setting. And so I also enjoy it quite a bit, and that's the benefits of it. The downside is I might have some gaps in my knowledge, and if you notice any of those, feel free to comment. Please be nice. That'd be cool. And we'll go from there. So today I want to talk about a newfound love I have of Schmitt Triggers. And that's going to be the title of this episode. My love affair with Schmitt Triggers. Now I'm kind of jumping the gun a little bit. I want to do an episode about digital logic and 7/4 logic and Boolean logic and analog versus digital voltage and how that is and how those are different. And I will do that. But just talking with a friend of mine on the phone, and he said he would watch this video if I made it. So here it is. At least I'll have one view, right? And got a whiteboard here now, because that helps with stuff a little bit. And I'm going to try to position my camera the best I can on my tripod here, and talk about Schmitt Triggers. Schmitt Triggers are so cool, man. By the way, if you want to watch videos that are really awesome on YouTube and probably going to be better than mine in a lot of ways, check out a user W2AEW. This guy is amazing. Can't recommend his videos enough. And he has a great video on Schmitt Triggers too. And so you might want to check that out even before watching this, if you feel like it. I'll try to break things down as well. So there's a little bit of prerequisite knowledge, and one of those is that you might, hopefully are at least a little bit familiar with 7/4 logic. Those are really old. It's a really old family of ICs, integrated circuits, from the 1970s, I believe, is when they were first developed by Texas Instruments. And there's a whole family of like tons and tons of circuits that are really the building blocks of all modern computers, microcontrollers, FPGAs, you name it. And so what's cool about learning this stuff is you really are learning the building blocks of how more complex circuits work, including your Arduinos, stuff like that. I've been having a lot of fun learning about this stuff. A lot of things that are taught as Arduino applications I'm doing instead with 7/4 logic, and I'm finding it very fulfilling and very fun. Here's an example of one circuit that I'm working on that's all in 7/4 logic, and I'll have more info on this later. It'll be updated on my website, and this actually uses a Schmitt trigger, as are a lot of my new designs, which is pretty cool. So let's go into it. Schmitt triggers. A Schmitt trigger is this symbol right here. It's kind of like a weird looking S, and there's an input and there's an output. So it's not like a NAND gate or an OR gate or an OR gate or something like that, where you have two inputs and one output. So you can do a lot with these, right? You can do all sorts of switching and stuff. And so you would think with just a simple input-output that you'd be pretty limited. But actually these do amazing stuff, a lot of applications. And this symbol, by the way, the symbol that without the S, the weird S thing in the middle, is a NOT gate or an inverter. And these are really simple. And please don't be too. I'm still, no expert at this stuff. So please, I hope you're not too intimidated when I'm drawing these symbols, because it's really not as complex. I want to encourage people to really dive into this stuff at their own pace, but it's really not as complex as I once thought, because I suck at math. But you can actually learn this stuff without knowing math really at all. It's just logic, dating back to old Aristotle, I think. So you have this symbol, right? And this is an inverter, which means that, actually this is a buffer, my bad. An inverter has the little circle on the end, though I guess you could draw it without it. A lot of these, some of these symbols have different conventions, so feel free to correct me in comments and all that. But basically, you have, if you have a zero, a digital zero, which let's say in analog terms, that would be ground, right? Or, there's different symbols for earth ground and digital ground and all that. So, or this is a zero, this is the other way to put it. And if this is zero, if this is low, then this output will be high. And that's really all it is. So if say you had a circuit that was plus 5 volts, right, and then there's obviously a ground. If this, the power pin going to this inverter is going to 5 volts, and then it's also got a ground, and you give this plus 5, then over here you will get ground. And vice versa. If you ground this, you'll get plus 5 on the output. So pretty simple stuff. The way that that's drawn, by the way, is if it's going from ground to 5 volts, then you would draw it like this, because on an oscilloscope, that's what the waveform would actually look like. And I can go into that more in a later video, but it's low and then it goes high. And there's a name, this line here is actually not real. Let me erase that a little bit better. I think they're called verniers, but actually it would actually look like that. And then there's a time differential between when it goes low to high. So don't, if that line in the middle confuses you, it's actually just for simple use of drawing it, essentially. But in reality, the voltage is low, and then it kind of climbs up very slowly, or very quickly, I should say. Sorry, to be a logic high. That transition though is almost instantaneous. So really, it's going low to high. And that transition in between here, for a regular inverter, let's say an HC, a 7404, is a really classic inverter. This transition time would be in the nanoseconds. Nanoseconds. This is really fast. And so, for all intents and purposes, we just put a line there. But it's good to know that that's not the reality. That's just what the convention is. So that's a basic inverter. And basic inverters they're okay. They're kind of cool, but they can't do a lot. They're very limited in comparison to a Schmitt trigger. So basically, if you're ever using an inverter for any circuit ever, especially if it's a 7404, you might as well just use a Schmitt trigger, because it's the same thing, only with more features, and it's pretty much the same price. I don't think it would cost that much more. If anything, a couple of cents, a couple of pennies. So hopefully that makes sense with the inverter. Likewise, I will say that if this input here is high, then the output will be low. And then how would it look? It would look like that, right? Your output would go from high to low when this input changes. So not much to them. That's inverters. They're normally used for, I've used them anyway, for clock signals and stuff. You're not going to use them a lot, I think, in day-to-day analog circuitry, doing DIY designs. Not as much, anyway. And so let's talk about Schmitt triggers now. And the most common Schmitt trigger, dating back to the 70s, is the 7414. And the family that most people use is the CMOS family. and that's the 74HC14. That's the one I recommend you use. There's a bunch of different family. When you change these letters here, is how the family changes, and that there's a lot of stuff that goes into that. I don't want to go into too much detail on that right now, but you can get a 74 LS14, and there's also 74 AC, which is, I believe, the really fast equivalent. There's differences there, and I can go into that in a different video, or you can look that up. But for all intents and purposes, we're gonna stick with the 74HC14. And so, what is the 74HC14? Let's give it a visual representation. It's that little dude. This is in the SOIC package. I think it's an SOIC. Yeah, it's an SOIC-14 package. This is bringing it in closer there. You can get a glimpse of it. And I think SOIC stands for small outline integrated circuit. I'm actually not going to spell all that, but it's small outline integrated circuit, and it's, I believe, the oldest package of a surface mount component. It's a very old package dating back to at least the 80s. These chips have been around a long time. And then, of course, if you want, you can find these. And if you're new to this stuff, I really recommend starting out with dip packages, which are very popular still. And they're nice and big and easy to work with. And this is not a 7414. This is actually a 7404 right there, which is the inverter we were just talking about. This is an inverter. And you'll notice it says SN in the beginning. All of Texas Instruments modern 7.4 logic chips, they put an SN in the beginning of the name of it. Not sure why that is, actually. But different manufacturers will add their own acronyms. So you might be wondering, well, there's only an input and an output, and then of course there's going to be power and ground. That's only 4 pins. So why does this have 14? Well, the reason is that each of these, both of these, and they're both 14-pin packages, have 6 of those. There's 6 inside. There's an input, output, input, output, input, output, input, output. So you get a bunch of them. And if you want to go the old 7.4 logic route, and you want to save money and get the original chips from the 70s, you're not going to find any with less than 6 of these built in. However, modern day, I don't know, maybe past 10, 20 years now, they do make single versions in a much smaller package, which I'll show you in a minute. But I'm going to be focusing on these packages for right now, because those are kind of the classics. Those are the old school. So let's erase a little bit here. So we have these 2 packages, and for almost all 7.4 logic, especially the modern stuff, that your pin 1, which is, of course, if you're looking at the package here, pin 1 is always going to be a circle or something, or sometimes with the dips they do a little indent like that. And so almost always your pin right above P1 is going to be your voltage input, or VCC, and your pin in the bottom right in reference to pin 1 is going to be your ground, almost always. And so with these, then you have an input and an output. Usually with logic it's labeled A and then Y. Y is usually the symbol for the output. And so as you go down the line, you have this might be A1, Y1, A2, Y2. And that's just to indicate that that's the second Schmitt trigger in the chip. And so you go around, and there's 6 of these in each of these chips, which is cool. You got more to work with. So let's talk about what makes Schmitt triggers so much better than just a regular inverter. The main reason is that Schmitt triggers have something called VTH, and it stands for voltage threshold, and it has to do with the on threshold. So when your voltage is rising here, this is a graph, right, of 0 volts going to 5. With all transistors, all circuits, there is a threshold for which it will be on or off. If it's above that threshold, it'll be on. If it's below, it'll be off. This is the case with all NPN transistors, PNPs, pretty much any transistor. Just because that's kind of how transistors work. And so that is great, except that sometimes you have stuff that might, this on threshold might vary a little bit. It might not be, let's say this is 2.5 volts, just for argument's sake. Depending on the run of the IC, or how hot it is, or other characteristics, that might be lower. Might be 2.1 volts. And so you don't have a definite threshold that you can rely on. In addition to that, Schmitt triggers are really great if you have noisy voltage around the threshold, or voltage that's moving around the threshold, because it can actually, say your voltage is doing this a little bit close to the threshold, it will actually keep it in an on state, and it won't change until there's a large enough differential between the off state and the on state. So what does that mean? That means that this chip is highly tolerant of weird on and off states, of stuff where it's not clear cut, digital on or off. This stuff is really tolerant of that, and which is really great for analog circuits, especially analog voltage. So that'll bring us into our first use of the Schmitt trigger, and that is as a debouncing circuit. I'm going to go over debouncing circuits a little bit. Debouncing! And this is one of those things where if you didn't learn about it and you ran up against it like me, you definitely found yourself needing to learn about it quite quickly. That is an E, by the way. Sorry! Boy, is my handwriting suck on that one. So, we all know that a lot of circuits, we have mechanical switches that we press to activate things, right? And pretty much anything in the physical world, especially it's interacting with humans, that's us, is going to have a switch, a button or a switch of some sort that will not look like this. Because when I press this, there's actually a tiny, essentially microscopic, in the milliseconds of a bounce time. And I could scope that out, but I don't really want to hook up my oscilloscope to scope all this right now. But basically what that looks like is, I'm trying to think if there's a way I can do that actually. Setting up a debounce circuit. Maybe I'll edit into the video later. So what that ends up looking like is if you want this, right? You want this to turn your circuit on, right? In reality, it's actually going to look like that. Because when I hit this button, there's a little plastic rod that goes down that hits a tiny metal disc, and it's a conical shaped disc, and it looks like, if you're looking at it from the side view, it looks like that. And you have a little center rod that's hitting it right in the middle of the conical disc, and then the disc essentially depresses. It's probably not a great drawing of it, but it essentially presses the switch down. Presses the switch, and then it releases it, depresses it. So that's your basic understanding of how a switch works. That's what's happening when I'm hitting this. This is hitting this, and because it's conical, it snaps and then moves back into its previous shape. Snaps, moves back into its previous shape. There's mechanical wear when you do that, which is why these all have a lifespan. And another anecdote, by the way, I'll just throw this in here. If you have one of these with a long vertical shaft for controlling it, a longer, I'm forgetting the technical term for it, but the longer shaft when you press down on these things, if it's got a longer one and it's not in an enclosure with a plastic cover to control it, and your finger is just hitting it, what'll happen is you'll hit these at different angles, and it'll bend this. It'll move this off center, off the disc. So this will go slightly off center, and when that happens, these discs will go out much sooner, much sooner, and you will get more bouncing issues like this, and not good. So what happens when you do this? What happens when you do this and you have a circuit that, like most logic circuits, it'll be really confused by this, because how it's interpreting this in its brain, basically. I know brain is not the greatest example, but it's basically interpreting this as that. It's going to interpret all these rise and fall times because there's that threshold we were talking about, VTH, right? And all transistors have that. And so as this rises and falls below a threshold, the chip gets confused, and it thinks that you're actually giving it multiple pulses. The fact that this happens almost instantaneously to our sense of time, when in reality it's, milliseconds or even nanoseconds this is happening, probably milliseconds, doesn't make it any easier, because we're like, oh, why is it acting weird? I heard it click. You hear that click, right? It's like, what's the problem? It should just be, boom, up. But in reality, there's actually a bunch of noise in there that you cannot physically see unless you have an oscilloscope. So that's what's going on. And like we talked about here with the Schmitt Trigger's ability to deal with noisy inputs, it makes it a perfect candidate for debouncing. So that's the first use of a Schmitt Trigger. And I'll go ahead and make a list here. So debouncing. And I'll give you a typical circuit for debouncing here. And there's a couple extra components you can add to make it even better. But let's say you have your switch. This is the schematic symbol for a switch. It closes, right? And one side is ground. Usually switches ground themselves. And we'll have a pull-up resistor. Usually, 5 volts, whatever your supply voltage is. And I've borrowed this. I should try to find the website that I've borrowed this from, because there's a few websites out there that, this is a common circuit though. It's used all over the place. And so this is usually a 10K, typical pull-up. A 1K here, and then also a diode. And so this is typical debounce circuit. Hey, I drew that pretty well. Look at that. So this is the noisy input going in, which we drew earlier. It would be something like that. Noisy part going in, coming out pretty much perfect, pretty much really clean. This is a 0.1 microfarad capacitor right here. And so how this works is when the switch is open, current comes through this resistor here, this 10K resistor, goes through the 1K, charges up this capacitor here, and when you hit the current down, hit the switch down, the capacitor discharges, and that cleans up the input going to the Schmitt Trigger a little bit. So this is actually optional. You could just connect this straight to the Schmitt Trigger and you will get some debouncing. But you do these two things together and you have yourself a kick-ass debouncing circuit where you won't have that kind of on-off, 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 on. And sometimes it won't even end up on, it'll end up off because it confuses the circuit. So that's the first use of a Schmitt Trigger, debouncing circuit. Good stuff. Good stuff. And I've used these a lot. Actually, I'm using these in one of my new boards I'm making where it's kind of a multi-purpose DIY board. I'm going to link my website in the description, and you can check out some of the boards I'm designing that are going to be up for sale soon. And pretty exciting stuff happening right now with things I'm making. So that's the first use. Second use of a Schmitt Trigger, which I can't actually demo for you. I have a circuit built for it right now. And this is cool. I found this out really recently. Is what's called an astable vibrator. Now, what that means is you're looking for a pulse that goes up, down, up, down, up, down, like that. And it just keeps going. These are super useful because this is essentially what a clock signal is. And depending on the frequency of how, and the speed of how fast the rise and fall times are, the rise time being that, obviously, fall time being when it comes back down, that will determine what your clock signal is. So these are used all over the place, very, very common. And in my case, I needed one of these to drive, for one of my recent projects, which I actually have a video about, to drive a Sega Genesis controller, which has a 74HC175 logic chip inside of it, and that will give you a different output of button press depending on the state of the clock. So when the clock's high, you get a button, for example. When the clock's low, you get a different button. To remember this right, actually, C and start. Let's use those examples. When the clock's high, you get C. When it's low, you get start. So anyway, these are very useful. The other thing that astable vibrators are very useful for, again using the video game example, because I do a lot of video game stuff, is autofire. Autofire, that's all autofire is. Anytime you're turning on autofire, you're hitting a button when you're hitting your controller button, and then it's doing this, right? It's doing a lot of button presses all the time. Now obviously that's simulating an analog person pressing a button, but the computer doesn't know any different. It thinks you're just hitting a button a bunch of times really fast. And then you can adjust the speed of this. You'd have a pretty awesome autofire, wouldn't you? And that's actually what my new circuit is doing, and that's what this knob is for right here. But more on that later. And so, a bunch of uses for this. Making an astable multivibrator is very useful. However, almost everywhere people have you using a freaking 555 to do this. And I learned this from a really great site, which again, I need to find all my sources and throw them up here. I apologize. But a 555, or the LM555 is the common one, made by National Semiconductor, now Texas Instruments. Boo! I don't like Texas Instruments. I missed National Semiconductor before they merged. Anyway, the LM555 is a really common chip. It's a 4-pin chip. 1, 2, 3, 4. It comes in SOIC, DIP, a whole bunch of packages. Really, really, really popular chip because it can do all sorts of multi-vibration stuff. The problem is, yeah, it's smaller, which is nice. Problem is, the Schmitt Trigger can do this. If you're using it for astable stuff, Schmitt Trigger can do the exact same thing, and in a package that's twice as big, you get 6 of them. 6. Whereas you can only make one astable vibrator with a multivibrator with the LM555. And not only that, LM555s are noisy, high power consumption. That's the huge one that I really don't like them for. And more external parts. Also more expensive in most cases. If you get a 7414, it's almost always going to be cheaper. It's not a proprietary part as much, too. It's, 7414s are much more of a building block. More versatility means usually lower price. Also just been around longer. So when you add all these up, LM555s start to look kind of unappealing. The advantages, of course, are LM555s do have more versatility as far as for vibrators, not for other stuff. They can do what's called mono vibration, one-shot vibration. There's more stuff you can do with these as far as vibrators, but what else? What's another advantage? So 4-pin package, if you only need one, and you don't want a 14-pin package, or sorry, 8-pin, I'm sorry. It's an 8-pin package instead of 14. So if you only need one, then, that might be a better way to go for you, and you're not going to reuse the other Schmitt triggers. What else? Maybe there's more information online would be another plus, more info. There's a lot of circuits out there. A lot of people love this thing, and it's good for some things. But you're looking at like a 10 milliamp power draw on one of these at 5 volts. And whereas a Schmitt trigger, you're looking at the 10 microamps. So far more power is required to run one of these, and it's problematic. Problematic in my case. So I was really lucky to learn about this stuff, because Schmitt trigger does the job for what I'm doing just as well. 555s are known to be slightly more accurate for some things. You can also adjust the duty cycle. The duty cycle, by the way, no, it is not poo. It's not the cycle of duty. Womp womp. Duty cycle is how much space there is in the changes. So like this would be a different duty cycle than this. If it's high here, the same amount of time that it's low here, that's called a 50% duty cycle. And as that changes, the percentage changes. So this might be a 67% duty cycle or whatever. That's the duty cycle. With a Schmitt trigger, and with auto fire and pretty much everything I'm doing, and with clock signals, you're almost always going to use a 50% duty cycle. In fact, I would say always, especially with auto fire. There's no reason you wouldn't. So a Schmitt trigger, by default, with its astable multivibrator, it's pretty much 50%. And we're going to look at that in a sec. How do we make a Schmitt trigger multivibrator? Real simple. Real simple. Get our Schmitt trigger there. We have a capacitor to ground. And that can range, but let's just say 0.1 UF. But it can range. We make a big range. And a resistor across the output. That's it. That's it. Now you have a 50% duty cycle astable vibrator, which you can use for your auto fire, even some clock signals if your clocks are not too picky, and other stuff. And let's take a look at it right now. I guess we've done the whiteboard thing for a while. Here is the circuit that I built a while back. Zoom in a little bit here. And this is also a Schmitt trigger. Excuse me while I adjust the camera. Oh, sorry, hope you didn't get dizzy with that. This is also a Schmitt trigger. This is one of the newer package types, and this is a dual Schmitt trigger. There's 2 in that package instead of 6, like the other ones. And that's an SOT 23-6 package type. So I'm going to turn on my bench supply here, and we'll see it oscillating. And the LEDs are hooked up inversely, so when one's on, the other one's off, vice versa. And you can see that it's 50%, about 50% duty cycle. They're on and off, same amount of time. Instead of a resistor, I have a potentiometer hooked up as a rheostat, and all that means is that this is a resistor that's changing resistance as I turn this, rather than using all 3 pins. If you don't know what rheostats are, you can look them up. They're spelled like that. Rheostat. And what's cool is as you change the resistance, then the frequency changes. As I turn it higher, it gets a lot faster. Makes for a perfect auto fire control. Very, very simple, low power, very easy. And it's doing this, for those that are curious, because it's creating an R, this is called an RC network, because there's a resistor and a capacitor. And the output is feeding the input, but there's a resistor limiting that, and it's charging up a capacitor at the same time. So when you're limiting the current coming in and you have to charge something, it does it slowly, and there's a delay. And so that delay, and then it goes back again, and then it delays, goes back again. That's what makes the astable vibration. And because it's a Schmitt trigger and not just an inverter, you only need one of them. You can do these with inverters, but you need 3 of them usually, and it's not 50% duty cycle. So because it's a Schmitt trigger, you only need one, and it's pretty darn accurate. And that's because, again, of that voltage threshold that it has, where it can account for the slight changes that come across on the input. Usually that's going to be due to the capacitor fluctuating, because the voltage isn't just going to go down instantaneously. A capacitor, the voltage will go down in a slope because it has to discharge analog voltage. It's not a digital circuit. That part of it isn't. This part is. It's a nice example of how digital and analog can work together. Work together as a team! So that's the A-stable vibrator for a Schmitt trigger. The last thing I'll share with you for Schmitt trigger, there's a couple other things actually. See if we have time here. Hopefully you're still with me. Hopefully you're still with me. But I looked up online and was really happy to find this page here, which I think is really cool. There's a modification that you can make to this right here, and this is found from robotroom.com. Apparently somebody's professor helped them draw this, where you can make a Schmitt trigger, here this is the AC one, it could be HC, LS, whatever, into a PWM pulse width modulation controlled output. PWM, you hear this term a lot. I didn't know what it was for a while. But what PWM means is that you can control the duty cycle by turning a potentiometer. Well, that's what it means in this circuit. I shouldn't say that. PWM means that the duty cycle changes. Pulse width, the width of the pulse is modulated. It changes. So as it changes, right, if it's high longer than it is low, let's say it's like this, right, then its output's going to be pretty much high. If it's low longer than it's high, let's say it's like that, the output's going to be pretty much low, right? So that would be an on or an off, more or less. As you change that, what happens is you simulate the movement of analog voltage. So say you had 0 and 5 volts. As you change a PWM, it actually looks like it would look like a slope like that if you're turning it at the same, if you're adjusting it at the same speed. So it's a way for digital circuits to imitate an analog circuit with some benefits. So for example, when a voltage rises and changes like this, a lot of motors, for example, don't like that very much. And they would prefer to just have it be like this, and see how it gets wider over the top over time? They would prefer that. Motors actually don't like to have different voltages sent to them. And DC motors is what I'm talking about here. But so that's what PWM does. It imitates, in a way, you know, it imitates in a way the how an analog voltage change works. So you see these a lot with these guys, cooling fans. Let's pull up one here that actually has PWM control. You see it a lot with these guys, where you have 3 wires. One's the plus, one's the minus. Obviously, grounding input, usually ground in 12 volts if you're using this with a home computer, home tower or whatever. And the third pin is the PWM signal, and it tells the fan how much to be on and how much to be off. And that's how you get fan control. Because it's a digital signal, the CPU can control that, and it can send it to the fan whenever it likes. And that's why your fan speeds up when it senses, oh, the computer goes, oh, temperature's rising, time to increase this PWM signal. In the case with our Schmitt trigger, I want to be able to control this with my fingers, not as a CPU. And if you build your own PWM this way, you can do that, which is really exciting. So yeah, thanks to robotroom.com here, you can do that. And let's draw that circuit. Probably have to erase a little bit, make some space here. And that circuit looks like And it does this, by the way, by exploiting the use of diodes, which limit current to one direction. Control the flow of current is a more accurate way to put it. So this example uses 2 Schmitt triggers. Really easy because you got 6 of them, right? No biggie. And let's make the little S thing so we know we're not using an inverter or NOT gate, as it were. So you got 2 Schmitt triggers, and the output of one is connected to the input of another, essentially as a buffer stage, and that's because it's using the VTH of the second one to clean the output a little bit. So that's always good. Might not be totally necessary, but it's good. And actually, take that back. It is necessary because it's going from the input to the output on this part, and it probably helps the signal quite a bit. So I'm just redrawing it from the website here that I just showed you. So the circuit looks like, see if I can draw this properly. So you have a diode going one direction, another diode going another direction. These are signal diodes. They could be Schottkys, regular signal, 41, 48. Doesn't matter that much. And then you have a capacitor to ground. And I think this is a great, it's kind of like a hack of the last circuit. That's what's great about it. That's what's really fun about these 7-4 logic circuits is there's so much you can do with them because they're the building blocks. And there's so much untapped potential for new designs using the same stuff. So I think they're really cool. And that's all it is. So how does this work? Well, we have our capacitor from the first one, right, that we're charging up and discharging. And we have the resistor that's limiting that capacitor from charging and discharging, right? So that makes sense. And so that makes our astable vibration, right? That makes our pulse go up and down. Then we have these 2 diodes. And we have the fact this is not any longer a rheostat, but it's actually a potentiometer, which means that this wiper moves closer to here or closer to here, depending on how we turn it. When it's closer to here, current is going to run through one of the diodes for one of the types of pulses, for the high pulse, basically. Will run through at a different amount of time through to this capacitor than it will going through the other diode when the resistance changes, because there's more resistance going to the high part than there is to the low part. When the knob turns, there's more resistance going to the low part than the high part, and that's because one of the diodes is always blocking. These are in reverse, so one of them is always blocking the other direction. And so this is a common technique used for 555, stuff like that, where you can take an astable and convert it into a PWM. So as you turn this, you will get, if you turn it in one direction, you will get wider, like that. As you turn it in the other direction, you will get wider lows, like that. I don't know if I drew that the best. So I'm not the best drawing PWM signals. So, but give these circuits a try. They're all online. And post back with your results. Let me know if your duty cycle varies a little bit. I've heard that over time you might have a slight shift in the phase of your clock pulse if you're generating it from a 555. I haven't tested that vigorously. It doesn't matter with my applications. That would only matter if you have a computer or something like that, a microcontroller that you're powering with a clock pulse, and it really needs a very specific clock pulse and it's time sensitive. Then these might not be the perfect thing for that. But for anything with LEDs and stuff like that, you are in good company. And last but not least, I'll show you a circuit that I just came up with tonight. So it's untested, but it should work just fine. It's a really simple circuit and another cool use of a Schmitt trigger. I had one of these extra on a board I'm designing, and so I thought I'd make use of it.
Basically what I wanted to do is make an LED, have two LEDs. One that would be on when the voltage is over 3.6 volts on a lithium-ion battery, and then off when voltage is less than 3.6 volts, and then have the other LED switch on instead. To have it be off when this one's on, vice versa. You can see where I'm going with this, right? You're inverting a signal, and you're also using an analog voltage that changes and turning it into a digital signal for an LED. What's really good at that? This baby right here, that's who. So yeah, I was pulling my hair out trying to find a cool example of this, and let's see if I actually can show you the one that I came up with. I actually built it right here. I found a lot of sites I was looking up, you know, simple LED battery gauge. You know, with just all I would get is these examples of using an Arduino, you know, using an ATtiny84 or something like that, and it's such overkill. Here's one, you know, someone's hooked up an LCD, and it's pretty cool actually. This one's going to have a lot of features. It's definitely more advanced than my project needs, but you know, there's so many overkill options for this kind of application, and I needed something really simple. So this one that I found online, and I can't find the site on my tablet right now, but uses a single transistor. And actually, I might actually just remember it. If I remember correctly, it looks, don't kill me if I get this wrong, something like this. No, it's an NPN. So it's the one that I just built. And this is it's where I borrowed the idea from. I think it's a really cool idea. It just isn't quite good enough for what I'm using it for. So this one, there's an NPN with a LED, right? A signal diode here, and then another, I'm going to erase some of this stuff at the top so I can finish drawing this. Another LED, I'm not going to fill that one in just so you can tell the difference between the signal diode. A resistor, and then these all go to 3.6 V or whatever, your VCC for a lithium-ion battery, which is what I'm using this for. The description says when the voltage is above 3.6 volts, this LED is on. When it's below 6 volts, 3.6 volts, this LED turns off, and this LED is on. How does it do this? Pretty simple actually, and pretty cool. It's exploiting the VTH of a simple NPN transistor as a switch, hooked up as a switch, and using the voltage drop of across an LED to do that. It's pretty clever actually. By the way, this in the bottom here is ground, and when this voltage is high, then when the base is high, the collector and emitter are going to be connected, and they're essentially going to be ground. So this LED is going to be grounded on both sides. Nothing's going to be on. It's going to be high because if the voltage here is high on the input, let's say it's 4 volts, then you get a 0.7 volt drop or whatever across this LED, another voltage drop across this diode, and then that's still going to be plenty of voltage to give a positive voltage to this to the base here. And there's this resistor where, you know, let's say it's like, I think it's like 1K in the example. So that'll give, you know, well over, you know, whatever it needs, 2 volts or whatever, to power this on. As the voltage drops, then the voltage is not enough, and this 1K resistor is actually going to be supplying ground, a low signal, to this base, or this NPN, in which case it turns off, and then the positive rail is pulled and powers this LED. How does this work in practice? Well, I can actually show you, because I have it all hooked up right here. And this does relate to Schmitt triggers. I'll show you in a sec. Just bear with me as we follow follow me down this rabbit hole. Let's see. Do I have this hooked up properly? Is my bench supply hitting me? Oh, gosh. Just reverse the polarity. That's what happens when you film while you hook up power supplies. But it's fine. It's just an NPN. It looks like it handled it just fine. So go over here, and I'll turn off this light so you can see it. And if the voltage is, this is actually around 3.1, 3.2, the resistor values are slightly off in my setup here. But pretty much you'll see it'll fade a little bit as I adjust it. And actually I'm going to try to get the bench supply readout in the picture as well here. So here is the bench supply voltage. This is on my nice little Wi-Fi readout here. It's pretty sweet. So the camera can pick it up. And I don't know if you can see that very clearly, but it says 3.16. And if I adjust it slightly, the LED the red one will slightly dim, and that's the one hooked up to the output of the NPN. But for the most part, it shuts right off. The green one, on the other hand, dims slowly over time because it's actually just dropping the input voltage. Once the input voltage gets too low, it's just off. And the other one comes on because it's going through a different circuit. So this example technically kind of works. It's kind of cool. I like the idea behind it, but I don't want a main power LED that gets dimmer over time. I just want it to be on and then the other one be on. And just have it, really quick like that, right? Because that just looks kind of janky. If your power LED is just dimming, I don't know. For some people it might like it, but I don't like it as much. And the other problem with this circuit is that you can't use a single bicolor LED with a common cathode to run this thing because they're totally different connections. So you'd have to use two different LEDs for this no matter what. Well, I wanted to use a single LED that has 3 pins on it as a common cathode, or use one of these really cool, let's see if I can show you here, one of these really cool red and green LEDs. Of course you can get them in different colors, where if I give it positive and negative, let's try to move the camera one more time here. On one set of pins here like this, I get green. You can see that all right. And then if I reverse the polarity, I get red. How cool is that? I think it's pretty cool. Because it's only 2 pins, which is really good for my design. Less wires, less hassle. So I want a design that could just switch those when the voltage gets low. And that's it. So I came up with this one with my wonderful Schmitt Trigger. With the wonderful Schmitt Trigger. And I'll share it with you. Like I said, this hasn't been tested yet, but it's pretty straightforward and I think it should work just fine. So you have a voltage divider on the input to the Schmitt Trigger. So when the voltage drops, your Schmitt Trigger will have a threshold will be activated and it'll switch from a low signal to a high, or I should say a high signal on the input to a low, which makes the output switch from a low to a high. So low to high, right? And then we have the output also feeding to another Schmitt Trigger. Again, this is easy because we have 6 of them in the package. Another Schmitt Trigger. And then we have our bicolor LED. Like so. And this resistor can be here or here. You just need one current limiting resistor for the LEDs, obviously. And it's pretty simple and accomplishes what I wanted to do perfectly. or it should once I build it. Once the voltage drops, this will go. This will be. Let's say this is a low and this is a high, and this is a low. Not explaining this very well. So if this part is high, let's say it's 3.6, and let's say this voltage divider is set up, and I'm not going to go into voltage dividers. You can look that up for another video maybe. But let's say this is 2.5 volts going in there, going into our Schmitt trigger, right? And that's around the threshold. So this will be a low output. In that case, this would be a 0, which would make this essentially ground to the this LED right here, the one on the right. And then this ground would become a high signal for the output here, which would make this high. So that would turn that LED on. This one's in reverse, so it's off. You have a current limiting resistor, so nothing's going to blow up. Then when the voltage here drops, when it goes down, then your ground is going to pull up to this guy, and you'll have a low input, and so then you'll have a high on the output because it inverts it. So when you have a high output, it goes to the other Schmitt trigger, becomes a low, and then this LED turns on. And that's it. Real simple. Real simple. The beautiful thing is my board already has a Schmitt trigger on it with 4 unused Schmitt triggers because I was using the other 2 for debouncing circuits. So how beautiful is that? And that's the beauty of having a bunch of them available like that and having them be cheap. So that would be... those are the examples that I've come up with just so far in the past month or 2. I'm sure there's many more to come. But let's run it down one last time. The things you can use a Schmitt trigger for. You can use them for debouncing. Very, very effective for that. You can use them as an astable circuit. Quite good at that. Not 100%, but very low power, very efficient. Third, you can use them as a PWM controller, using as a LED dimming circuit, using them as a fan control, all kinds of stuff. And then fourth, battery indicator. Let's say battery fuel gauge indicator or low battery indicator. That's what that is. There's always names for it. And those are just 4 off the, off the recent pile. So that's my love affair with Schmitt triggers. That's why I am just so in love with those people right now. They're not people. It's an IC. But Schmitt triggers. They're awesome. Check them out. They're super cheap. 74HC14. Get yours today. Hope you enjoyed this video. If you want more of these, let me know. Check out my website and enjoy building stuff. This is Sega Sonic Fan, signing out.